Hello everyone, and welcome to another Mini Sky Tonight. So, happy World Space Week. So, every year NASA hosts World Space Week where they do a topic based upon space and how it's improved our lives. This year, it's satellites. So, I decided to do a presentation about the history of satellites, what they are, the different orbits of satellites, and how they have affected our lives throughout the years. So, let's dive right into it. So, what is a satellite? The broad definition of a satellite is any object that goes in orbit around another celestial object. So, in the case of planets, planets are satellites of a star. Moons are satellites of a planet, and so on. So, anything that goes into orbit around something else is, by definition, a satellite. Now, when we think of satellites, however, it's the man-made electronics that we put up into space. So how do they work? So the image I have here is a basic television studio to a dish network kind of television because it was the easiest representation I could find. But it's a little more complex than that, but here's the basic idea. So you have two stations on Earth that want to communicate through radio broadcast, but they're so far away they can't. And the reason being is because since the Earth is curved, sometimes the radio broadcast can't follow along the curve very well, as well as the signal gets so spread out over the distance that it becomes so faint that you can't hear it. So you need somebody as an intermediary in between that long distance to be able to accept the signal and pass it along. And the easiest way to do that is either to put somebody in the middle of there, which then you start having the problem of, okay, now we're going to have too many radio communicators across the United States or across the world, or you put something up into space. And that's what we've done. So basically, you could have a television studio that's broadcasting, like, say, for example, your favorite sports team. And so what they do is they send the signal as an uplink to the satellite. From there, the satellite relays the transmission and converts it into a downlink, to which then goes into your television or your computers as you see. So how do we get them up there? Well, obviously we launch them into space through different means, but the idea of putting something into orbit came long before we started launching stuff into space. It started off with Newton. He created this thought experiment of, okay, he saw some cannons being fired by the military, and he noticed that they kind of make a curve before they eventually land. And he thought, okay, what if we had a much more powerful cannon? And so he got to see a more powerful cannon fire, and obviously it went farther, but it still curved down to the Earth. And that's when the wheels started turning in his head. So he realized, okay, if we had a super, super, super powerful cannon, eventually it could be so powerful it can leave Earth completely. But what if we have that sweet spot cannon to where we can fire at just the right speed to where it can go all the way back around the Earth? Or in this particular case, make an orbit that it's going so fast that Earth's gravity can't pull it down. And that's the concept of a satellite. And it was through this kind of mathematics and this understanding that allowed us to be able to put things into space. So what are satellites used for? Why are we sending stuff up into space? Well, obviously, traditionally, we've used it for weather, we've used it for understanding our planet, we've used it for radio and television broadcasts. The military uses it for communications, and also today, I don't know about you, I highly depend upon my GPS to get anywhere that I'm not familiar with. But with the newest updates in technology, especially now that we've been in COVID, we use it for global telephone connections, basically global networks, communications in remote places, and much, much more. So as technology has advanced, so has the need for satellites. So let's dive into the history a bit of how it all started for a satellite and how we got into the satellite race, so to say. It all started on October 4th, 1957, with the launch of Sputnik 1. Now, this was the height, kind of the Cold War era, so to say. where Russia and the United States were kind of staring each other down to see who would be the first one to flinch. And Russia was the first one to launch a satellite into space to promote their superiority. And this kind of struck a nerve with a lot of United States citizens. And so they were trying to scramble to keep up with them. But shortly after, a month later, they released Sputnik 2 with the dog Laika. So the first animal that's ever been in space was a dog. And it was shortly a year after that, or a few months after that, we released Explorer 1. So Explorer 1 was the first satellite by the United States, which is the picture in the bottom right. The picture on the top left is that of Sputnik 1. So the space race kept going and going. It was in 1960 that we launched the first weather satellite, TIROS-1. It was this kind of experimental weather satellite to basically help understand our weather patterns here on the Earth. And that's the image almost in the direct center there. It was this weird mirrored kind of satellite that allowed it to be able to view with different instruments at different angles. Then in 1961, Russia took the first step of doing the first human flights, and Yuri Gagarin became the first human to orbit the Earth. So in a way, he was the first human satellite, so to say. Then in 1962, the United States launched Telstar. Telstar was the first telecommunications satellite. And it's that image on the top right. It looked like a weird orb in a way. But from these concepts of being able to launch different types of satellites and different types of people up into space, and it opened the door for other countries to be able to do the same. Today we have India, China, Japan, European Space Agency, most of the European countries, New Zealand, and several more countries have launched a satellite into space. So what started off as a fight between two people turned out to be something good because it opened the door for other people to launch information up into space. So where does it travel on from there? Well, in 1971, we launched our first space station, and this was a huge step for the Russians as well as mankind's exploration of space. The idea that you could put something into space for long periods of time to where people could live in space for longer periods of time. The next satellite that was launched that was a major breakthrough was Landsat. It was the first global surveyor type of satellite to image our Earth and see how it looks. And from 1973 to 1979 was the United States version of Salyut 1, the first space station, Skylab. And that's where we did a lot of different experimentations for the United States that then would lead us towards being able to develop the International Space Station, which you can see near the bottom. 1974 was the GOAS, the Global Observatory satellite. And basically it allowed us to be able to image our Earth in so many different fashions, not only taking pictures of the Earth, but it also did weather and much, much more. So basically it was the first step towards understanding how our planet worked. In 1981, we had the space shuttles developed, so where we can send multiple people up into space rather than having to depend upon a Saturn V rocket. From 1986 to 2001, the Mir space station was in operation, and that's where we did a lot of collaboration with Russia to be able to understand space. So it was the kind of the first endeavor of having international collaboration. Rather than us duking it out, we realized, yeah, this is starting to kind of get expensive. And in order for us to be able to develop things further, it's easier to work together than it is to duke it out. In 1990, the first telescope was launched into space. So before then, we just had satellites that just imaged different things. And it was the Velar satellites, which were the first gamma ray satellites that were initially developed during the Cold War era because they didn't want to do nuclear testing in space. So they put these Velar satellites up into space to make sure that nobody was launching nuclear weapons into space. But it was from that those two satellites that we discovered that there were things that were going on in space, which then prompted the need of taking a telescope that's was originally on the ground and sticking it up into space. So Hubble Space Telescope was the first actual real telescope to be launched into space. And then in 1994, you had the first GPS constellation. Now, for many of you younger kids, back in the day, so this is something you can ask your parents. Back in the day, they didn't have a cell phone or a GPS to help them navigate. They had something that was known as an atlas or a map. This folded up piece of paper that you had to follow little lines and hope that the map was updated and hope that there was no construction on certain routes that you were trying to get to, or you accidentally went on the wrong route in order to get anywhere across the United States. I don't know about you, but I remember one time having to navigate via a map, and oh boy, was it hard. Because I can remember driving with my husband at the time across the United States, and I was following along the map very well, and then we hit a detour. And I was trying to guide us back or try to guide us around a different path, and I got us lost by accident because I thought I knew the directions I was going, but because the routes had changed so much from the map I was reading, I got lost. But fortunately, the invention of GPS, the GPS constellation having all these different satellites allowed me to be able to get a GPS for the first time, and I now know exactly where to go. So what does it mean by GPS constellation? I'll describe that in the next slide. And then of course you have the International Space Station, the first big, huge collaboration with many different organizations to allow people to stay into space for a long period of time. In fact, to this date, we have over 19,000 satellites in orbit from different countries for different purposes, etc. That's a lot of satellites. So as I was describing earlier, what is a constellation? Well, like sometimes what we call a constellation is basically little points in the sky that basically create a shape. Well, these satellites are in constant orbit that they sometimes look like they're in a certain position or shape. And the reason being why they have to have so many is because they have to cover a wide, broad area of the Earth. So that if one satellite is out of range, the next satellite will come into range. So that way you have close to complete coverage of the Earth. So we have all the different types of satellites based upon what they're used for, but where are they located? So let's describe the different types of satellites based upon their orbits or their frequencies. So the first type of satellites are what are known as geostationary Earth orbit satellites. They're 35,000 kilometers above the Earth's surface and they kind of go along the equator. So they stay in one relative position for a long period of time. So you basically have a 24-hour view of one particular area. So it stays in that one position. And since it has a large covered area, it can almost cover 1/4 of the Earth's surface, which is really helpful. And it's ideal for satellite broadcasts and other multi-point applications. Disadvantages is that because it's so high above the Earth, the signal is relatively weak, and there's also a time delay. Now, why is there a time delay? Now, keep in mind, imagine the little space between my fingers is a little bit of a signal, and that little bit has to go beep, 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 several kilometers up above the Earth. Even though it's traveling at a relatively fast speed, it's still a long distance for that to travel. So there is a bit of delay to travel that many kilometers up and that many kilometers back down. Also, the problem is it has difficulty with the near polar regions because since it's so close to along the surface of the equator, once you start getting the curvature towards the poles, it doesn't quite reach. So let's look at where's the next one to do. Low Earth orbit. So the ones that are really, really, really close to the surface. So roughly between 500 to 1,000 1,500 kilometers above the Earth's surface. So they're the ones that are on barely the outskirts of our atmosphere. And they travel really fast. They have to travel really fast because since they're so close to the Earth, they have to travel fast enough to where Earth's gravity doesn't pull them down. So you're only able to see them for about 15-20 minutes each pass. So they go really, really fast. The advantages of having these ones is that better signal and less of a time delay because they're really close. And since it's a smaller area that they cover, you have less of a bandwidth having to send signals up and back and forth. Because keep in mind, it's sending a signal in a cone and sends a signal out in a cone. So sometimes the wider area means you're sending out a cone to nobody versus when you're sending a signal in a small little designated area, less bandwidth lost. Disadvantages is that they are very costly. You have to have multiple of them in order to keep coverage across the entire globe. And also you have to deal with the relative problems of Doppler shift. Now, for those that don't understand what Doppler shift is, it's basically, imagine you're hearing a car siren. And as it's coming close to you, it's getting louder and louder and louder. And as it's going away from you, it's getting softer, softer, softer. That's Doppler shift. It's basically the compression of sound waves and they start to get louder and the separation of the sound waves as it gets farther away. And since these satellites are going so fast, you have to deal with that. As they're coming closer, it gets louder, and then as it goes away, it gets softer. Also, you have to deal with atmospheric drag. Keep in mind, they're on the bare edge of our atmosphere. So there's just enough of a bit of an atmosphere that could cause drag on them and cause them to deteriorate their orbit where they could eventually fall down to Earth. So you have to have some of these satellites, but what can we do as an intermediary? Why not medium? So instead of having something that's very far out or something that's very, very close to Earth, we can have something that's in between. These are visible relatively for 2 to 8 hours each pass. So which is really nice because that means fewer satellites are needed and it can cover a larger area over a longer period of time. Disadvantages is since it's a medium, has a weak signal, not as strong as a low Earth orbit or a LEO satellite, but it's stronger still than a GEO satellite or a geocentric orbit. So other types of orbits that are used are high elliptical orbits. They were mostly used by Russians to get close towards the poles areas. And then you had high altitude platforms. Basically, these are the lowest of the lows. Basically, these are your blimps or your high altitude weather balloons, sort of say, that do kind of coverage. They're cheaper to put into position, but we require a lot of them to put in a network. And also you have the problem where you can't keep them up there for a long period of time. So there's that problem. But nonetheless, we have put things into orbit. So here's just a rough idea and schematic of where these different orbits are. So you have geo orbits that are the furthest out, the medium orbits that are in the middle, and then you have the ones that are really close, the LEOs, and then the HEOs, or the high elliptical orbits. Those are kind of in between the MEO and the LEOs. So what about frequency bands? Well, not only do you have to worry about where to put them in orbit, you also have to do different types of satellites in different orbits based upon their frequency. Because the stronger the signal, the more you're able to push out more information. Problem is that if it's a low signal, you have to be closer into the Earth in order to be able to get a signal in. So these are some of the different types of bands that satellites use today, depending upon what they're trying to do. And with all that in mind, this is a lovely image of all the satellites that are in orbit. I was able to create a model using Digistar of all the different satellites that are in orbit as at this point. As you can see, it's a huge mess. But it's needed for what we do today. So what's the point of having all these satellites? Well, it gives us better communications. A better understanding of our planet gives us these beautiful images that we can observe our planet as it evolves, as well as understand how our planet works in general. And it allows us to peer into the distance from our own backyard and not having to be able to depend upon sending things to space out further away from the Earth, but rather just stay close to home and still explore our universe. So what's next? As I showed you in the previous image before, we have a ton of junk up there. So is there any way to better utilize those satellites in different ways? Believe it or not, we have been working on it. Many of the satellites back in the day were huge. They were almost double the size of school buses today. But now, with the advancement of technology, we've created these things that are known as cube satellites for telecommunications. They're literally about the size of your toaster. It's mind-blowing, right? That the fact that these huge satellites that used to cover up almost half of a football field, some of them, are now so tiny that they can fit in the size of a toaster with the advancement of technology. So with this in mind, several organizations, including NASA, have come up with ideas of how to get some of the old satellites that are starting to become retired or out of commission, because sadly, many satellites still stay up there. So we have to figure out a way to get rid of the excess material that's stuck up there so that A, it doesn't hit anything, B, we're not putting junk up into space. So especially ESA has taken a headway on this particular adventure where they come up with this unique program called the eDeorbit. Basically, it takes this unique type of satellite and it launches out a net, and then it captures the dead or soon to be retired satellite, and then the satellite gently drags the dead satellite into a safe orbit where it can crash land down into the Earth, into a safe place to where it can then be either fall into the ocean and or recaptured for spare parts. And then we launch a new replacement satellite, hopefully one that's much more advanced and or smaller to reduce the amount of junk that's up in space. And of course, the Japanese have come up with a couple ideas too, including electronic tether, where they would send out a ship out into the middle of the ocean and send out a beacon and gently pull it down towards the Earth. Again, all in the works on that one. And of course, one of the things I'm looking forward to, the next space telescope, James Webb, which will be much more powerful than Hubble Space Telescope and will be able to help us explore further out into space. So needless to say, satellites have been an important part of our lives and they helped change the way we live today. So with that in mind, folks, if there's a topic you would love for me to cover over, leave it down in the comments. If there's a question you would love for me to answer, leave it down in the comments as well. Also, parents, if you're looking for some fun activities for your kids, futurereadysa.org has a wonderful site that allows your kids to do some fun activities and to earn digital badges. I highly recommend the Astronomy Plus one because that's one of the ones that I've worked on. And also check out our website at our SAC SCOBY website to be able to check out our SCOBY to Go monthly publications to where you can see some other fun activities as well. So until next time, stay safe, stay healthy, and always never stop learning.